Oh, welcome back to the wonderful world of calculus. And I know that's what you think as well, so I'm just going to leave it as that. All right, so heading into 5.3, looking more into our study of definite integrals and antiderivatives. We're going to start really just scratching the surface at that antiderivative, even though technically we've kind of looked at it already, looking at what makes the derivatives and that sort of stuff. We'll look at a few things here. All right, so start off with a big page for you. This is some of our rules for definite integrals, and actually I have 2 pages. I think there are 7 if I counted correctly. And the first like 5 rules here are pretty basic. The first one is if you find the integral from b to a, it's just the opposite as if you found it from a to b. And you can kind of just, it's the same area, it's just in the different direction. So that's why we call it the order of integration. If you try to find the integral from a to a, that's like finding an area of a rectangle whose base is 0, which comes out as 0. So you note here that they say something up here about these two things being definitions. So these are definitions that we're going to use. All right, so constant multiple, there's two they're basically the same thing here. The first one just says if you have a constant multiple times a function in your integral, you can take that constant multiple out, something along the lines of 0 to 5 of 3x dx is actually equal to 3 times the integral from 0 to 5 of x. And we can make this statement. It actually comes out sometimes a lot easier. And continuing down here, we have the one, just the negative. If you have the negative of a function, it's just the negative of the integral. The sum and difference, this is very, very handy for us, just like the sum and difference property was for derivatives, which means now we can find the derivative of a really kind of ugly polynomial. If you had, let's say, from 0 to 5 of x squared plus 3x minus 1 dx, you could actually break this up into the sum of 3 different integrals from 0 to 5. We could go from 0 to 5 of x squared dx plus 3 times 0 to 5 of x dx plus, actually minus because it's a minus here, minus the integral from 0 to 5 of 1 dx. So it would be a constant. And we could actually break it up and find different areas here. Obviously, the x squared piece is a little bit hard for us because we haven't really found the antiderivative for this yet. All right, so that's the sum and difference identity. I call it identity, but it's rule. Okay, and then the additive rule as well. You'll notice here what this actually is saying. If I find the integral of f of x between a and b, and then from b to c, really b is the same number because b equals b. So we can actually say it's the integral from a to c. It's like breaking up an interval for no reason. It's like saying, hey, walk from here to across your room and then across your room to the bathroom. When I could have just said, hey, walk to the bathroom. All right, very, very simple. The next couple rules are kind of complex looking ones. And the first one is the min-max inequality. So if max of f and the minimum of f, so it's like max and min of the function are the maximum min values of f on a to b, then we can say the minimum of f times b minus a is less than the integral, which is less than the maximum f times b minus a. And there's some things that we're going to be doing with this, showing that the integral here is going to be between two numbers, which can basically say, hey, what's the integral here? Well, the integral could be between -2 and +1. All right, showing max and min. And then the domination is kind of along the same line. If f is bigger than g on a to b, then the integral of f and the integral of g also follow that same inequality. And the same thing, if the function is bigger than 0, then its integral is bigger than 0 as well. And these are actually kind of obvious. If you think about the first part of the domination, if I had a function f of x here, and I found the area between a and b, or the integral between a and b, you could see that this area is that big. And if I had the function g of x here, you'll note that f of x is greater than g of x for all values on a to b. And you will probably see that this blue area is smaller than the red area you would get from f of x. And likewise, if f of x is bigger than 0, so you look at a function where it's fully above the x-axis, here, and you look at an area, you can tell that the integral is also going to be above 0 because that shows an area of something bigger than 0. All right, so there's some of our rules that we're going to be looking at. A couple examples that I want to see, and they're going to give you some stuff in certain problems like this, and you might even see this kind of thing on a AP exam. So it tells you the function, the integral of the function between -1 and 1 is 5. The integral of the function between 1 and 4 is -2, and the integral from 1 to 4 is 7. Of a different function, by the way, this is h of x, is 7. And we want to use some of our rules to help us figure out what the answers to all of these 6 things are going to be. Well, the first one, question A, it says find the integral from 4 to 1 of f of x. Well, you look over here, and I have the integral from 1 to 4, and one of our properties says if we change the order of integration, it becomes the opposite of the original. So we have 4 to 1 f of x, which is actually the opposite of 1 to 4, which is just the opposite of -2, which is 2. All right, so that kind of easy one there. What about the second one, from -1 to 4? Well, I don't have anything from -1 to 4 here for f of x, but I do have -1 to 1 and 1 to 4. So for B, from -1 to 4 of f of x dx, I can actually split this using our other property that, I can't remember what they called it. It is the additive property. There we go. I can break this up into -1 to 1 f of x dx plus 1 to 4 f of x dx. And I know to go from -1 to 1 for the function f is 5. And to go from 1 to 4 is -2. And I get a value of 3. Again, kind of straightforward there. All right, so now we get a more complex one here in C. And we're just going to use basically the constant multiple, because you notice this 2 here, and the sum and difference rule for integrals. So I'm not going to rewrite this whole thing here, but I can first rewrite the sum. And then I can kind of use my constant multiples here. So 2 times the integral from -1 to 1 of f of x dx plus 3 times the integral of -1 to 1 of h of x dx. And now it's so simple, right? Because f of x from -1 to 1 is defined as a 5. So I get 2 times 5 plus 3 times, let's see, 7. And I get 10 plus 21 is 31. All right, what about E? Or sorry, Miss D here. What about D? 0 to 1 of f of x. And I hope you're trying to just think about this. I'll go, well, oh, this is just half of this interval, so it should just be half of this answer. But that's not true. So if that was you, get that out of your head. All right? Because if we had a function and going from, oh, I guess we got to go from -1 to 1. And let's say it was down like this and then just leveled off. Well, from -1 to 1, this is actually going to be a bigger area than from 0 to 1. And just this little simple picture right here actually shows you why it can't be half of this area here, because this is a counterexample. This is what I mean by a counterexample. I found one area where this wouldn't work to be half of this. Okay, so you notice here it says find each of the following integrals if possible. So D is not possible. It's not half of the 5. Which actually goes the same for -2 to 2 for h of x. h of x goes from -1 to 1 in our definition for the integral. And I can use kind of the same reasoning here. If I have -2, -1, 1, and 2, if I had some sort of function here, and let's just say this was a nice simple parabola, right? And then you might be thinking, oh, well, it's actually 4 times, is that 4 times the distance? So 4 be 2, oh, I guess it's twice the distance. It's twice the distance, should be twice the area. But again, I'm going to use kind of a, well, what if the function did this on both sides of the 1's? Well, this doesn't look really like twice the distance, or I mean, double this area. I could do all sorts of different things that would make it look like this wouldn't work. I could do all sorts of things that make it like it would work, but not in these cases here. So this one, can't do D, can't do E. Can we do F? Well, you might be thinking, oh, I could do part of F, and you're right, you can. You can break this up into -1 to 4 f of x dx plus -1 to 4 of h of x dx. But then there's a problem. We know what this is, the f of x piece. That's -2. But we don't know what this is. We have no definition for the integral of h of x from -1 to 4. That's a bummer. We can technically, if you want to think about it, we could go a little bit farther than that even. We could say it's actually the integral from -1 to 1 of h of x dx plus the integral from 1 to 4. Oh, I'm sorry. I was not paying attention to myself. That's -1 to 4, which means from -1 to 4, we actually define that for b is actually the sum of these two things. So that was actually 3. My fault there. We actually define that to be 3 to go from -1 to 4 because it's actually the sum of 5 and -2. Sorry about that. And if we continued this kind of process for h of x, we could get down to this piece here that is defined, but we can't get this again. We can't get this 1 to 4 for h of x dx. So again, that one's going to be not possible for us. Another quick question here. Maybe not quick, who knows. Show that the value of this integral is less than 3/2. And this is going to go to our min-max inequality. So what I first want to do is I want to figure out what's the maximum value of this function that's going to happen between 0 and 1. So I need to figure out, for this function, square root of 1 plus cosine x dx, where is the maximum value going to occur? Because I want to show that this value is less than 3/2. Well, on this particular function, without the integral here, square root of 1 plus cosine x, when x is, actually it doesn't really matter, the max value for this particular function is square root of 2. And there's different ways you could probably figure this out. You could probably figure this out calculator-wise. Well, if the max value for this function is root 2 is 1.4, well, 1.41, whatever, and this is 3/2. So I already know that 1.41 is less than 3/2. So I can show, using our min-max inequality, I can say the integral from 0 to 1 for the square root of 1 plus cosine x dx is less than or equal to square root of 2 times a minus b, or b minus a, whatever here, which is root 2. So it tells me, using my min-max identity, if you want to call it that, the function itself will never go above square root of 2 between 0 and 1, which will actually show, using this inequality, that, using transitivity, by the way, this integral will never go above square root 2. And since square root 2 is not above root 3, or not above 3/2, that means this function is never going to go above 3/2. So you can kind of add this in here. We did a little bit of this last year, so kind of look at this statement. This is actually a true statement because the integral is less than this thing using our identity. This thing is equal to root 2, and therefore the thing is less than root 2. And we could actually say it's less than 3/2. We're actually pretty legal in all of those steps, as to my understanding for all math. All right, so let's go ahead and go forward here. We got a few things we got to still cover. Those were just kind of some of the good examples. Be very cognizant of those rules, because those rules will never leave us, especially those first 5. Those first 5 are going to become just kind of a mindset to you when we get to harder and harder integrals. All right, so first, average mean value. So we're going to kind of just use some of these formulas. Not a whole lot of examples of what I'm going to be doing, but if f is integrable, remember that word, you can integrate it, on a to b, then its average value on that interval is given by a very simple formula. The average mean value, you might remember that name from earlier. The average value of the function is given by 1 over b minus a times the integral from a to b of the function f of x. Really simple. They're going to ask you, hey, what's the average value of this particular function over this interval? Pretty simple, straightforward question that they can ask. Kind of like this. Find the average value of f of x equals 4 minus x squared on the interval from 0 to 3. So I can just go like this. 1 over 3 minus 0, the integral from 0 to 3 of 4 minus x squared dx. Now, we don't know how to do this very quickly or accurately outside of the calculator, so some of you guys be very happy to do this on a calculator. So it's going to be 1/3 times this thing on a calculator, and that's math 9 if you are unfamiliar with this. The integral here is actually 3, so I get the answer of 1. And that means my average value is going to be 1. And the next question that's going to be asked on here is, oops, come on, come back. Okay, sorry about that. The question to be asked in here, does f of x actually take on this value at some point in time in the given interval? So I want to know, will 4 minus x squared ever become 1? I don't know. Let's see. So 4 minus x squared, does that ever equal 1? Well, that's super simple for all of us. Subtract 1, add squared or add x squared. You take the square root, you get plus or minus. Oops, that's stupid. Sorry, not stupid, ugly. Plus or minus square root of 3 is equal to x. That tells me that that happens at plus or minus root 3. Well, actually on the interval, square root of 3 is on this interval, and therefore it happens at x equals square root of 3, not the negative version. So it does happen. So the average value is 1, and it does actually happen on this interval from 0 to 3. And that actually leads us to the theorem for the mean value. So we have a mean value theorem for definite integrals, just like we had a mean value theorem for derivatives and continuous functions. So it basically says exactly what that last question stated. If f is continuous on a to b, then at some point in time c, or some point c, on that interval, f of c is equal to that average value. It's exactly like the question we just said. We just went about it the other direction. So back here, I could have said, does f of x actually take on this value at some point in time? You could have automatically said yes if you'd have known this theorem. Because this theorem states that it has to have happened. All right, so this is a mean value theorem. This is very important for us. A lot of theorems, they just kind of show up in the AP test, and you're kind of surprised sometimes when they show up. Because you're like, oh, wait, what was that mean value theorem? Forget already. But you needed it in order to prove something. All right, don't think you got out of proofs just because you're in calculus. All right. So here's where we're going to connect to the antiderivative. There was a little exploration that they do on page 289. It's called Exploration 2. And what they basically lead us down into is if you take the derivative of the integral, notice we take the integral from a to x, we actually get the function f of x. So the derivative of the integral is the function. It's basically what that's saying. Well, that kind of might be kind of intuitive to you because they're kind of like inverse things of one another. And this leads us to the integral as an antiderivative. So basically saying if I took the derivative of this big f of x plus c, remember c is a constant, if I took the derivative of this, that would get f of t on the interval from a to x. Or the other way of saying this is the integral from a to x of f of t is big f of x plus a constant. And we were actually doing this before, looking at, hey, if this is f prime, what could have been f of x? And it's basically going this direction. If I gave the integral from a to x of sine t dt, I could say, well, what makes the derivative of sine? Oh, the derivative of sine is going to, whose derivative is sine? Oh, that's negative cosine. All right, we're going to be doing a lot of this, so you start being comfortable with going in the wrong direction here. All right, so which leads to this. This is huge, okay? This is huge. The integral from a to x, or something to something, basically, of f of t dt is big F of x minus big F of a. Now, we could actually put a b in here. It's big F of b minus big F of a, and it's going to help us evaluate integrals. I always say antiderivatives sometimes. It's going to be able to help us evaluate integrals using a basic antiderivative. And obviously we're not even, or still, like I said, we're just scratching the surface for antiderivatives. They get harder and harder as we get going here. So let's just start with this one. You might remember what the actual answer to this is because we've used this tons and tons of time, because they just say, hey, It's equal to 2. Use it. But let's actually figure it out. So from 0 to pi, for sine of x, that's just this little bubble here. And what I want to do is I want to think about, like I said on the last page, whose derivative is sine of x? Well, I know that if I took the derivative of cosine of x, I would get negative sine. But I don't want negative sine, I want positive sine. So I should probably take the derivative of negative cosine. So this is going to be the negative cosine, using this from up here, negative cosine of x. Well, that's the top number, so it's pi, minus negative cosine of the bottom number, which was 0. And, oh, look at this. You might want to remember some trigonometry in your study of calculus. Wow. Who's been telling you that for the last year or so? All right, so cosine of pi, if you recall, cosine looks like this. Here's pi. Here's 2 pi. Pi halves, 3 pi halves, 0 is actually all we need to know, right? So cosine of pi is negative 1. So negative 1 minus, actually it's plus, right? So it's minus and negative makes plus. Cosine of 0 is 1, which is equal to 1 plus 1, which is, oh, look at that, 2. So you've just actually finally been able to prove that this is 2 using a very simple, I don't really like calling this a formula, but it kind of is. Really simple concept of antiderivatives and integrals. All right, let's look at one more kind of like this, and I kind of made this one up, so hopefully this one works okay. Let's find the integral from 1 to 3 of 2x plus 1. Now, I know we can do this using a trapezoid, but I want to actually do this using this new process, right? So let's think about whose function has a derivative of 2x plus 1. Well, I know that if I took the derivative of x squared plus x, that will come out as 2x plus 1. Here you actually notice I didn't say anything about c up here, because the c is going to be, it's going to be like plus c, and you're just going to subtract them. So they actually end up going away, which is kind of nice when you're doing definite. Remember, this is called definite integrals because it's defined between 2 points. So I want to actually do, okay, so f of x. So I want to do x squared plus x. Oh, but I forgot. I got to evaluate this at 3, right? So I can't actually do that. I got to evaluate at 3. So I have to do, okay, this thing evaluate at 3, which is 3 squared plus 3, minus this thing evaluated at 1. So I get 1 squared plus 1, and I get 9 and 3 is 12. Plus 2 is, sorry, not plus 2. Minus 2 is 10. And I really hope that's what comes out as the area. You can kind of do that for yourself if you want to. 2x plus 1 is going to look a little bit like that from 1 to 3. My base is 2, or sorry, my height is 2. My bases are, let's see, 7 and 3. Oh, look at that. 1/2 times 2 times 3 plus 7 is 10. Yay, we got the same answer. Always like when that happens. All right, so, if anything that you come away with today, I really hope you come away with this and the beginning identities. All right, take care. See you guys tomorrow. Have a good day.